Hello, everybody. Thank you for coming. Today, we have the pleasure to have here Milen Yakimov from Yosemite State University. He's going to talk about the Poisson geometry of large quantum groups. Thank you, Milen.
Thank you, Guillermo. So I want to start by saying that I'm very grateful for this invitation to give a talk at the seminar at Córdoba. This is a joint work with Nicolás and Iván, and with Nicolás Andruskiewitsch and Iván Angiono. And I have learned a great deal about Hopf algebras from this work. So it's a great honor for me to give the seminar in one of the best places in the world for doing Hopf algebras. I'm very excited about it. And in this talk, I want to describe some work that we did with Nicolás and Iván, where we managed to construct a bridge between the theory of Hopf algebras on one side and on the other side, Lie theory like Lie groups and Poisson geometry on Lie groups. And the goal of this work is to find a Lie theoretic or Poisson geometric method for studying the irreducible representations of Hopf algebras. In particular, this family of Hopf algebras is going to include as a very special case quantum supergroups at roots of unity. And this framework will produce a method to study the irreducible representations of these important objects using Lie groups and Poisson geometry. And for the first time, this was done in a series of very influential works of the Concini-Kac and Procesi from the early 1990s. And I want to go over these very important developments first, and then come back to the subject of Hopf algebras and explain exactly how everything fits in that framework. So in the early 1990s, the Concini-Kac and Procesi constructed a family of quantum groups at roots of unity, which are called big quantum groups. And they found a way to study the irreducible representations with the methods that I mentioned, namely Lie groups and Poisson geometry. And I want to say more about these fundamental works of the Concini-Kac and Procesi. So the starting data is G is any complex simple Lie algebra, and epsilon is a primitive nth root of unity, where n has to be odd and it has to be co-prime to 3 in the case of G2. The big quantum group that is associated to this complex simple Lie algebra G is a quantum group which is by taking the usual relations for the quantum group and just writing epsilon instead of Q. So the big quantum group associated to SL2 has generators K, E, and F, where they satisfy the relations that are written on the bottom of this slide, right here. And epsilon here is just any root of unity of order that's odd. The punchline in the methods of the Concini-Kac-Procesi is that they were able to construct a very large central subalgebra of this quantum group. The central subalgebra is generated by the end powers of the Lustig root vectors. These are just quantum analogs of the usual root vectors that you would see in the universal enveloping algebra of G, together with the Cartan generators K1 through Kn. And it's somehow very similar to the situation that when you study the universal enveloping algebra of a simple Lie algebra over a field of positive characteristic. And then the Concini-Kac and Procesi proved that the quantum group, the big quantum group, is actually finitely generated in free module over this central subalgebra. And the goal here is to describe all irreducible representations of this quantum group. And these irreducible representations enter in a number of subjects that have nothing to do with quantum groups, like topological quantum field theory, invariance of knots and links in three-dimensional manifolds. So there has been a lot of interest in understanding exactly what are the irreducible representations, what classifies them, and what are their dimensions. The warning here, of course, is that the full center of this quantum group is bigger than the center of subalgebra. For we have the usual Casimirs, which are in the full center, but they are not going to be in this center of subalgebra. Now, the small quantum group of Lustig actually appears in a very easy way from this big algebra that we deal with. If we look at the maximal ideal of the central subalgebra that's generated by the n powers of the Lustig root vectors, together with the Cartan generators ki raised to power n minus 1. So this is a maximal ideal of this central subalgebra. Then when you look at the factor of the big quantum group by the centrally generated ideal, I'm sorry, this should be called an epsilon here, not a zeta, that's an epsilon. Then this is precisely the small quantum group of Lustig, which is a finite dimensional Hopf algebra. And people in Lie theory have been very interested in understanding the irreducible representations of this particular finite dimensional Hopf algebra. Furthermore, if we replace M0 in the definition of the small quantum group of Lustig, if we replace that M0 with any maximal ideal of this central subalgebra, we're actually getting a bundle of finite dimensional algebras over the maximal spectrum of this central subalgebra. That maximal spectrum is nothing but an affine space times a torus. And to every such maximal ideal, we can associate this finite dimensional algebra. So in other words, we have this bundle of finite dimensional algebras. And the intuition of the Concini-Kac-Procesi was, let's not study the small quantum group of Lustig individually. Just study all these fibers and try to understand the irreducible representations of the fibers by the geometry of the underlying space and by using the generation method to go from a generic fiber to the special fiber that defines Lustig's small quantum group. Actually, now this goes into a subject that has been greatly developed in the 60s, 70s, and 80s by mathematicians, including Procesi, Artin, Kaplansky, and Posner. And the setting here is that A is any complex algebra, which is a module finite algebra over a central subalgebra Z. In other words, A is a finitely generated module over this central subalgebra Z. And just like in representation theory, the big question here is, how do we describe the set of all irreducible finite dimensional representations of the algebra A? This is a completely general picture. And for instance, if you're doing modular representation theory for Lie algebras, then this fits in this picture as a very concrete kind of algebra A. Now, by sure, the first thing that you can prove here is that all of these representations have to be finite dimensional because the algebra A is a finitely generated module over the central subalgebra Z, which is assumed to be Noetherian. Now, by Schur's lemma, you immediately get that on each of these finite dimensional representations, Z is going to act by a character. And this immediately tells you that you have a canonical fibration from the set of all irreducible representations of the algebra A to the maximal spectrum of the central subalgebra Z, where to each representation V, you associate the maximal ideal of Z that kills that representation V. So in other words, we have this nice fibration picture where on the bottom, we have the max spectrum of this commutative algebra Z. On top of each maximal ideal, you have the fiber that consists of all irreducible representations that are killed by M. But if you think, what does it mean that an irreducible representation is killed by M? That means that this is actually a representation of the algebras that appeared on the previous slide, the algebras of the sort A times mod A. So in other words, we have the geometric picture, but on top, we also know that each fiber has a very nice representation, theoretic meaning. It's precisely the irreducible representations of the finite dimensional algebra A mod MA. This kind of picture has been studied by all these people, and there is lots of general results that have been proved in this full generality. If we're in the world of the Concini-Kac-Procesi, where A is a free module over the central subalgebra, we have an additional ingredient, these algebras A mod MA, they actually form a bundle of finite dimensional algebras over the base. However, people realize that that's not a necessary ingredient. In general, you can work with a sheaf of algebras, and then in the same way, the fibers of this fibration, of these irreducible representations, are nicely constructed in terms of the stalks of that sheaf. Now, I want to say something more about the techniques of the Concini-Kac-Procesi. So they came up with an extremely important notion of a Poisson order that puts furthermore Poisson geometry in this picture. So now we have a complex algebra A. We still assume that it's finitely generated module over the central subalgebra Z. But now we assume that we have two other ingredients in the picture. And the first ingredient is that Z on its own is a Poisson algebra. So it has a Poisson bracket, meaning that it has this bracket that satisfies the Jacobian, the Leibniz identity. But furthermore, the punchline is that we have an ingredient that links the Poisson geometry of that Z to the irreducible representations of A. And it's a very simple ingredient. This ingredient says that if you look at the Hamiltonian derivations of this Poisson algebra Z, which by definition is just the brackets with a given element Z with anybody else, each of these guys can be extended to a derivation of the non-commutative algebra A. If you think about what this really means, it gives you a device to connect the Poisson structure of Z to the non-commutative algebra structure of A. So it's a kind of datum that on the one side, it's semi-classical in the sense that it's in terms of Hamiltonian derivations of Z. But on the other side, it's quantum because it links derivations of A to the semi-classical structure Z. And the big theorem of the Concini-Kac-Procesi, which was axiomatized in this setting by Brown and Gordon, is the following. If you start with any Poisson order, and if you take two maximal ideals M and M prime, which are in the same symplectic clef of the maximal spectrum, so we assume that Z is a Poisson algebra, which means that the maximal spectrum is going to be a Poisson affine variety. So it's going to be an affine variety with Poisson structure. If they happen to be in the same symplectic clef, actually the two algebras that are obtained by quotiening by these central rated ideals by M and M prime are just plain isomorphic to each other. And this is a very strong statement. As a consequence of this strong statement, we actually get that there is a dimension preserving bijection between the two fibers of psi that are sitting on top of M and M prime. In other words, you can connect one fiber of irreducible representations with another fiber of irreducible representations in a way where you match the corresponding dimensions. So in other words, look at this picture, these 2 points M and M prime here cannot be in the same symplectic clef because over the point M, we have 4 irreducible representations, and over the point M prime, you only have 3 irreducible representations. So if you are in the same symplectic clef, these two fibers should be exactly the same, meaning same number of points and same dimensions of irreducible representations. The power of this theorem is that if you work in general with an arbitrary Poisson variety, it is partitioned, it is stratified into these symplectic clefs. And by knowing that everything is the same over the same symplectic clef, you can very frequently get that you actually have finitely many different kinds of such finite dimensional algebras. So all of a sudden your problem, which was a very infinite problem, becomes a very finite one. And this was somehow the big intuition of the Concini-Kac and Procesi, that they were able to build in a concrete situation of big quantum groups this very strong machinery that uses Poisson geometry to say that the irreducible representations are going to be one and the same for many points when these points are in the same symplectic cleave. Now you can ask the question, okay, that seems like an interesting notion of Poisson order, but how frequently does it appear in mathematics? And the next thing that the Concini-Kac and Procesi found, this was actually known even before them, that this kind of notion appears very, very in a very general kind of situation, and that is in the setting of specialization. So we say that an algebra A is a specialization if there is a complex algebra R and a central element H, which is not a zero divisor, such that the algebra A is a quotient of R by the ideal, the principal generated by H. And every time this happens, the pair of the algebra A and its center has a canonical structure of Poisson order, which is given by some really easy formulas. If we denote by pi the projection from R to the quotient, I'm missing here A, so this quotient is the algebra A. And if we pick up any linear section of A to R, this is a section of this projection. In general, we don't need this section to be an algebra homomorphism, and it will be interesting when it's not, and in pretty much any case that I know it is not. Then we can define a Poisson structure on the whole center of the algebra. So here Z is the whole center of the algebra, by saying that the bracket between two elements Z1 and Z2 is simply pick up their pre-images. Now, if you take the bracket between those pre-images, it would have to be in the kernel of the map pi by simple argument. And because H was assumed to be not a zero divisor, we can divide that by H, and then we can project this back to the algebra A. It's a very simple exercise that this indeed provides the structure of a Poisson algebra on Z. And furthermore, that strange ingredient of this map that extends the Hamiltonian derivations of Z to algebra derivations of the non-commutative algebra A is also given by pretty much the same formula, where we take pre-images, we take the brackets in the algebra A, R, where it's the one that's before the specialization. Again, it's proved that that gadget is divisible by H, we divide it, and we project it back to pi. So I want to say that in our particular situation, you can play this game in many situations. You can play this in prime characteristic. You can play this over the integers. In our situation, because these are quantum algebras, our central element H will be something like a free variable Q minus epsilon. And our algebra R would actually be not just an algebra over the complex numbers, but it will be an algebra over the Laurent polynomials in that extra variable Q, where we localize by a bunch of denominators and we watch out those denominators not to be the Q minus epsilon that we want to divide by. However, the big warning here is the full center that appears everywhere in this picture is usually going to be singular. And it's well known that doing Poisson geometry with singular manifolds creates lots of problems. And in order to resolve all those problems, we always have to find a large smooth Poisson subalgebra Z inside the full center that is going to turn the pair AZ into a Poisson order. And in concrete terms, what this means is that you have to a smooth subalgebra Z, which at the same time is closed under the Poisson bracket. So now I can say a little more about the Concini-Kac and Procesi. So the first thing that they proved is that the big quantum group is always a specialization. So therefore, if you look at the pair of the big quantum group and its full center, automatically it's going to be a Poisson order. However, at the moment, we have no idea what kind of Poisson structures are involved there. The next thing is this center can be very singular. So we have to get rid of the singularities in order to be able to study the representation theory efficiently. So the next thing that they proved is that these big central subalgebras that we saw on the previous slides, generated by the n powers of the Lustig root vectors, they proved that those happen to be Poisson subalgebras of the full centers. And then the third part is that if you look at these large central subalgebras, that they're going to be isomorphic to the coordinate rings of some algebraic groups, which are simple algebraic groups, and they will be equipped with Poisson structures that are of what are called standard type. So those are the ones that appear in the work of Drinfeld and Sklyanin when they did inverse scattering on the semi-classical level. So out of this, they were able to prove that if you look at all these central quotients, in a way, they're going to be constant along conjugacy classes of the group G. So this provided a huge reduction to the problem of studying the irreducible representations, because we got this invariance along conjugacy classes. So now I want to say next, what are the kind of results that I wanted to describe in this talk. So in the late 1990s, Andruskiewitsch and Schneider initiated a very powerful program, which is probably the major driving force in Hopf algebras at the moment. And this program is about classifying finite dimensional or not finite dimensional pointed Hopf algebras. I want to provide an intuitive introduction to the underlying notions, but I want to say at the moment that instead of giving the technical definition of pointed Hopf algebras, I want to say that every Hopf algebra that's generated by group-like elements and skew-primitive elements is an example of an algebra in this class. And most of the Hopf algebras that you come across, they have this property. They're generated by group-like elements and skew-primitives. So all I want to say from my observation, every important Hopf algebra that I've seen in my life is an example of an algebra that appears in this classification program of Nicolás and Schneider. So in that program, there is a very large family of infinite dimensional Hopf algebras, and we're going to treat this whole family. And inside this whole family, we see as very special cases all multi-parameter big quantum groups at roots of unity, the objects that the Concini-Kac and Procesi studied, all multi-parameter big quantum supergroups at roots of unity, all of them appear in this family. There are also exceptional families that can be viewed as quantizations of finite dimensional simple Lie algebras in prime characteristic, but these are quantizations over the field of complex numbers. So for all of these algebras, we're going to describe extensions of the Concini-Kac-Procesi results, and we will have underlying Poisson geometric and Lie theoretic objects that are sort of governing the representation theory for these algebras. In particular, we will provide this framework for understanding the irreducible representations of all quantum supergroups at roots of unity, which was sort of desired from point of view of mathematical physics. Our methods also very much differ from the Concini-Kac and Procesi methods, because the Concini-Kac and Procesi, they always relied on concrete calculations with Poisson brackets and reductions to rank 2 cases. Reductions to rank 2 cases because the Serre relations for Lie algebras involve only 2 terms. However, if you look at the quantum Serre relations that appear in the description of these algebras, there are 13 different kinds of additional Serre relations compared to the classical ones. And they go all the way up to 4 generators. So if you were to pursue exactly the method of the Concini-Kac and Procesi, you would have to do these reductions case by case for all 13 kinds, all 13 families. And in some cases, you wouldn't reduce to rank 2 subgroups, you would reduce to rank 4 subgroups, which is sort of really, can be extremely involved. So we designed this very general method that uses perfect pairings between different integral forms of these algebras. they're called restricted and non-restricted integral forms. And out of those pairings between integral forms, we can build this bridge to Lie theory without any ad hoc calculations of Poisson brackets, just purely using the perfect pairings between these integral forms. And in particular, in the case of the Concini-Kac-Procesi, we get new proofs that are different from theirs. So now I want to say a few words about the different family of algebras that appear in the classification of pointed Hopf algebras. And I want to be sort of very explicit and not really say things that are sort of very technical. So each of these pointed Hopf algebras, by some general result, is a deformation of a smash product. A smash product is simply a Hopf analog of a semi-direct product of Lie groups. So think about this as an easy analog of semi-direct sum of Lie algebras and the corresponding operation on the universal enveloping algebra. Think that this is just an analog of the universal enveloping algebra of a parabolic Lie algebra, where you have the semi-direct sum between the Levy factor and the new radical, and you want to link the universal enveloping algebra of the parabolic in terms of the universal enveloping algebra of the Levy factor and the new radical. So that's the kind of object that appears in this smash product, except that the second term over here is the group algebra of a group G. The first term here is the Nichols algebra of some vector space, and that vector space is called a Yetter-Drinfeld module for the group G. I want to say a few things about this object because they're sort of super easy. First of all, the best understood case up to date is the case of an abelian group G. And for an abelian group G, a Yetter-Drinfeld module is something that's very easy. It's a G-graded G module. So you have a group G, an abelian group G, and you're just looking at all G modules that happen to be G-graded, graded by the same group G. So in other words, V is going to be direct sum of submodules Vg, where each of these guys, Vg, is a G module. And then we say that V is of diagonal type if the abelian group G happens to act by a character on each of them. If you're in the world where the group G is not abelian, the structure is slightly more complicated. Each of these subspaces Vg is not a G module on its own, but G somehow moves these modules from one to the other by using the conjugation action on itself. So here's an example. And in this example, G is going to be the free abelian group on n generators. So it's going to be called Z to the n. I just want to ask, do you still get the connection that I'm showing, the slides?
Yes.
Perfect. So there's something going on with my iPad here and I don't see it on my iPad. I just wanted to make sure that it's a problem of the iPad. So here is this really super easy example, which is at the heart of everything. So G is the free abelian group on n generators. The generators are called alpha 1 through alpha n. And then the group algebra of that free abelian group is nothing but Laurent polynomials in n generators k1 through kn. So if we pick up a matrix of size n by n, whose entries are non-zero complex numbers, then we can form a very easy kind of Yetter-Drinfeld module, which is direct sum of n one-dimensional subspaces. On each of them, the generator ki just acts by rescaling. That's the character that we have in mind. And each of these one-dimensional subspaces is a graded submodule that's associated to the generator alpha j. It's not difficult to show that in some sense, if you enlarge the group G, this actually covers all Yetter-Drinfeld modules for a finitely generated abelian group G. And you can just pass from any other to this one by simply enlarging the group with some cover of the free abelian group. And that's pretty much all. So in a way, this is not really an example, but in a certain way, it kind of covers everything. So here's an example. If Cij is the Cartan matrix of a Lie algebra G, and Di are the standard symmetrizing positive integers that are relatively prime to each other, the ones that are 1, 2, 2, 2, and in the G2 case, you have a 3 somewhere, then the corresponding matrix that you can take out there is simply the power of epsilon that's given by Di times Cij. So that on top is just a symmetric matrix because the integers Di symmetrize the Cartan matrix. And we will see how this, what kind of objects, what kind of algebras this matrix produces after that. The next example is if you want to do a super SLMN, then you take again Qij to be symmetric, and it's given by formulas like this, which are pretty much the formulas that you would see for the Cartan matrix of type SLMN, but everything is raised to power epsilon. Everything is power of epsilon raised to what you would see in the usual situation. Nichols algebras are also something that's very easy, but they also playing a fundamental role because in a way Nichols algebras provide a fundamental framework for treating quantum set relations in a way that's not case by case. So in other words, if you want to go from quantum set relations of Lie groups to Lie supergroups or to some more general objects, all you have to do is run this machinery of Yetter-Drinfeld modules and Nichols algebras, and then this kind of set relations can be treated from a conceptual point of view, not by just case by case. So here is my set relation for SL2, it looks like that. Here's my relation of type B2, set relation of type B2. Here's how it looks like. They're all special cases of this general machinery of Nichols algebras. So if I start with a Yetter-Drinfeld module V, it's a braided vector space. In other words, it has an operation that flips the two coordinates, but it places this extra scalar Qij in front. And then the tensor algebra V, it's just a free algebra on the vector space V. It happens to be a Hopf algebra in this category of braided vector spaces. So by definition, the Nichols algebra is the maximal possible quotient of this Hopf algebra. So you look at any ideal that sits in degree 2s, 3s, and higher degrees, and then you ask what's the maximal possible ideal for which this is still going to be a braided Hopf algebra in the same category, and you prove that there is a unique ideal of this form, and you name the corresponding object Nichols algebra. Because it appears in this very intrinsic fashion, there are many ways of describing this ideal by some sort of general words. For instance, it can be described as the kernel of some bilinear form. It can be described as the kernel of some symmetrizing operators. So there are many different ways to describe this ideal corresponding to the Nichols algebra, but not explicitly, but rather in terms of general objects. For example, if we run this whole machinery on the previous matrices, so these are the braiding matrices in example 1, they look like that. In example 2, they look like that. If we run this machinery for them, we get precisely the positive part of the small quantum group of Lustig of any type G. And if you do this, for example 2, you get the positive part of the small quantum group of type SLMN. Should we make a pause here for questions, or it's the best is if I just go? I'm happy with any solution.
So, are there any questions so far? Yeah, maybe we should go on then.
Perfect. So the big question in the program of Nicolás and Schneider was for what Yetter-Drinfeld modules V The Nichols algebra BV is finite dimensional. And it was first solved by Nicolás and Schneider under some assumptions, which were fairly weak assumptions, but that was not like in full generality, so under some mild assumptions. And then Heckenberger came up with a solution of this in full generality. And what's important is that in the Heckenberger's work, he managed to introduce Lie theoretic objects that's associated to each of these Yetter-Drinfeld modules. He associated a root system that goes with each of them, a Weil groupoid that generalizes the Weil groups of Lie algebras and the Weil groupoids of Lie superalgebras. And also he introduced Lustig isomorphisms, which are generalizations of the Lustig braid group action. The Lustig braid group action is on the quantum group. All of these are on the sort of analog of the small quantum group for any of these braiding matrices Q. And these gadgets are simply the Drinfeld doubles of these smash products that appeared on the previous slide. And the way we view this now is that these are vast generalizations of small quantum groups, small quantum supergroups, but now they all appear in one uniform framework. Furthermore, Iván and Angiono came up with a sequence of very strong papers where first Iván introduced the notion of Cartan roots inside all roots. So these are analogs of the even roots of Lie superalgebras. And the complement of them are analogs of the odd roots of the Lie superalgebra, or better to say, of the odd roots for which the bilinear form vanishes on them, isotropical roots. So furthermore, Iván managed to come up with explicit description of the Nichols algebra. So this is like an analog of the positive part. This is like an analog of UQM plus. So he came up a description of this analog of this UQN plus, but this vast generality of what's the original picture, in which he proved that the relations for this Nichols algebra are certain complicated cell relations, which come in like about 30 different flavors, not just 2, 3, or 4 different quantum cell relations like in the classical case, but like more than 30 types of relations on more than 2 generators, together with power relations where each root vector raised to some power is 0, together with relations, this is for the Cartan roots, so think about even roots, together with relations for the simple roots, ei raised to power ni equal to 0. And then Iván defined this very important notion of distinguished pre-Nichols algebra, which is an intermediate quotient between the free algebra, the tensor algebra on V, and the Nichols algebra. And these are the factors of the tensor algebra, or the free algebra, by the complicated cell relations, together with these relations that ei raised to power ni will be 0 for non-Cartan vertices. So think that these are just the analogs of isotropic odd roots. And all the other relations, A alpha raised to power n alpha, are taken out of the picture. So now I want to tell you between this important notion of pre-Nichols algebras and the quantum world. So if we look at the double of the bosonization of this pre-Nichols algebra, this smash product, these are now vast generalizations of big quantum groups. So if we were to do this with the braiding matrix, just from example 1, we will get precisely the big quantum groups of the Concini-Kac-Procesi on stage 1. So we're going to call these large quantum groups simply because they apply to a large family. So these are not going to be bigger than the big quantum groups in the classical case. They will be just members of much wider family that includes the big quantum groups as very special cases. Then we can look at the large quantum Borel subalgebra, which is nothing but the smash product that appeared on the previous slides, but we use the pre-Nichols algebra here. And finally, if we look at just the distinguished pre-Nichols algebra, that is going to be a quantum analog of the positive part of the big quantum groups. And we're going to call this large quantum unipotent subalgebras. So on the left side, we have these Hopf algebraic objects. And on the right side, we have the classical counterparts in the theory of quantum groups, where we start with something that's like a quantum analog of the universal enveloping algebra, of the unipotent radical, of the new radical of the Borel subalgebra. Then we have a quantum analog of the universal enveloping algebra of Borel, and then we have the quantum analog of the whole universal enveloping algebra. For example, if we run everything in example 2, that's something that has not appeared before, we get exactly the quantized universal enveloping algebra of type SLMN that previously appeared in the works of Benkart, Kac, and Kashibara, except that we don't have a certain parity element, and then there is an explicit relationship between our generators and the generators of Benkart, Kac, and Kashibara. So in a nutshell, we just run the whole Hopf algebraic machinery here, and we recover the quantum SLMN as a very concrete example. So there's one extra assumption that we're going to make, and this assumption is that if we look at this braiding matrix Q, we will assume that it belongs to a one-parameter family. In other words, we can write down a braiding matrix that depends on one parameter. This parameter will be called nu. The matrix will have the form where I write down an integer times an integer power of this nu. And we assume that our braiding matrix Q is obtained from this matrix Q with the extra parameter by simply setting nu equal to epsilon. And to continue the dictionary, our large quantum groups, they're going to have generators like before. We will call them E, F, K, and L. There is a small technical detail that we have two copies of the Cartan subalgebra. In certain situations, we can remove that extra copy of Cartan subalgebra, but it's not a problem all the time. So in some way, instead of working with the Lie algebra G, which is a simple Lie algebra, we work with the reductive algebra, which is G plus H. So all that appears here is sort of quantum analog of the universal enveloping algebra of the reductive algebra G plus H. Then we're going to have relations that very much look like the previously studied relations, but now we're going to have a crazy set of Serre relations between E and F, and we will never write down those Serre relations simply because we will not work with the Serre relation, but we will work with this interpretation in terms of Nichols algebras and pre-Nichols algebras. So in other words, what is really the major difficulty in working with Lie algebras and Lie superalgebras, when people have to work in terms of these Serre relations, that will be handled by general machinery in terms of Nichols algebras and pre-Nichols algebras. And the rest is going to look like pretty much like the picture from Lie theory, where we just have the usual relations between the Chevalier generators H, E, and F. And again, we can write down some root vectors, E beta and F beta. These beta are going to be all the roots, the Heckenberger's roots for this Nichols algebra. We can write down PBW bases for the positive parts and the negative parts. And for the non-Cartan roots, we have relations of the form E beta raised to power n beta equal to 0. And for people who work on Lie superalgebras, these are precisely the kind of relations that you have for isotropic odd roots. So here is the first theorem. Each of our large quantum groups is a specialization of a non-restricted integral form of UQ. So in other words, our big UQ that depends on this parameter Q is an algebra over the field of fractions of this variable Q. We have to write down some integral form, and we can specialize that integral form. And this would make UQ together with the full center UQ. This is our big quantum group that's going to become a Poisson order. So far things are very similar. to the Concini-Kac and Procesi. The next part is in the works of Iván Angiono, before he was able to construct the central subalgebra ZQ, which is somewhat similar to the one by the Concini-Kac and Procesi, where you take powers of the root vectors, E, F, and the Cartan generators K and L. And the statement is that UQ is always going to be module finite over the ZQ, and ZQ is always going to be invariant under the Lustig isomorphisms. This is going to play a key role in the future developments. These isomorphisms between the different UQs or the braid group action is going to preserve the central subalgebras. So I should say that there is a small technical detail here in the case of SLMN. In the case of SLMN, UQ is not really module finite over the central subalgebra. We have to introduce one extra Cartan generator here, and I will just disregard this problem for the rest of the talk, just because it will make things slightly more technical instead of more transparent. So only in the case of SLMN, one has to introduce one extra generator here, because ZQ has dimension one less than what's needed. And then finally, the ZQ is actually a Poisson subalgebra of the central subalgebra with respect to the Poisson structure that comes from this specialization. So what we wanted as first step of generalizing the Concini-Kac-Procesi, we have it here. So the pair of UQ and ZQ is a Poisson order. And one thing that I want to say is, again, here we take a completely different approach to the Concini-Kac-Procesi, and the real difficulty is in step 3. So we have some abstract Poisson structure that we built on the central subalgebra, the full center of UQ. How do you prove that something very explicit is a Poisson subalgebra of this full center? The Concini-Kac and Procesi did that by an explicit calculation. What we do is the following. If we look at ZQ plus, that's the portion of the center inside UQ, we prove that it's precisely the fixed subalgebra of the center of the full center under a set of skew derivations which descend from the quantum group with the extra parameter. So we prove a theorem that every time you have a specialization, and inside that specialization you have a central subalgebra that's precisely given as the fixed points of skew derivations, it's immediately a Poisson subalgebra. So by running a general theorem like this, we avoid any calculations with this Poisson subalgebra, but we just refer to a general fact. And then in the second part here, we proved that our central subalgebra is invariant under the Lustig isomorphisms. If we apply all the Lustig isomorphisms, we actually take everything from this central subalgebra inside the positive part, and we can recover the whole special central subalgebra ZQ. And since these Lustig isomorphisms, they preserve the Poisson structure, we immediately get the third part of this proposition, that the central subalgebra is a Poisson subalgebra of the full center. And again, this is done without running any concrete calculation of Poisson with Poisson brackets. So now we have the following. I'm already at 12:51. We started a little late, but I will try to finish for about 5 minutes. So I'm sorry, I'm running about 3 minutes over time. I have 3 slides left, so I just need about 5 minutes to cover the rest. So now from the previous slide, we have Poisson orders that are related to the large quantum group UQ and to the analog of quantum Borel. So this is the UQ greater or equal than 0. So these are the large quantum Borels and the large quantum groups. Inside we have the center, the special central subalgebras. The central subalgebras are Hopf algebras, but at the same time they are also Poisson algebras. So then if we look at their maximal spectrum, they are going to be algebraic groups, because these Hopf algebras are automatically integral domains. These gadgets are going to be connected algebraic groups. And because of the Poisson structure, this will be algebraic groups with a Poisson structure. In other words, there will be examples of what are called Poisson algebraic groups, which means that these are algebraic groups with a Poisson structure for which the multiplication map is a map of Poisson varieties. So the next theorem is that if you look at these algebraic groups, you would be always able to find a semi-simple algebraic group of adjoint type. We call that GQ. So that if you look at these algebraic groups, MQ and MQ greater or equal than 0, MQ greater or equal to 0 is precisely the Borel subgroup of the semi-simple algebraic group of adjoint type. And MQ is a product of the positive and the negative Borel subgroups of this particular algebraic group. And furthermore, we can say explicitly what are the corresponding Poisson structures. So there is a classification of Belavin and Drinfeld that says what are all possible Poisson structures on an algebraic group GQ, which is simple. In this particular situation, it's of adjoint type. And our theorem says that they come from this Belavin-Drinfeld classification in a special case where there are triples classifying these Poisson structures called Belavin-Drinfeld triples, and those have to be taken to be the empty triples. But these are not the standard Poisson structures in general that would appear in the work of the Concini-Kac-Procesi. They're somehow more complicated structures. So now I want to say a little bit about the corresponding argument, because when the Concini-Kac and Procesi prove the second part here, they have a large number of direct calculations, just plain direct calculations where they compute Poisson structures, and they say that in order to verify something like result number 2, they have to reduce to all possible cases that give the Serre relations, and the Serre relations for finite dimensional simple Lie algebras are of 3 different types. These are Serre relations of type A2, Serre relations of type B2, and Serre relations of type G2, and they simply check all possible reductions. It's plain impossible in our situation because we have 16 other types of Serre relations that involve even more than 2 generators. So this case by case is simply impossible to be done even for Lie superalgebras. So I misspoke. There are not 16 other relations. There are 13 other relations in addition to the 3 kinds of Serre relations that we already have. So what we do here is that for each of these quantum groups that appear in the specialization, we're able to define what are called restricted and non-restricted integral forms. And we're able to define a perfect pairing between these integral forms. So then we prove that when we actually compute the tangent Lie algebra of these Poisson algebraic groups, it becomes a Lie bialgebra because the Poisson structure gives a Lie algebra structure on the duo. So when we compute these duotangent Lie bialgebras, we can fully describe those in terms of the restricted specialization. So everything before was in terms of this non-restricted specialization. That's what's giving us the whole picture of the large quantum groups. But the restricted one actually governs precisely this tangent Lie bialgebras. And from this restricted integral form and the perfect pairing, we're able to prove that the duotangent Lie bialgebra of MQ, let me just move the cursor up, just waiting for this black thing to disappear, exactly. So then I'm on the bottom of the slide, we're able to prove that this duotangent Lie bialgebra of MQ is precisely isomorphic to the Lie algebra of this adjoint group GQ. So that's a way that's producing the final result without doing any of these calculations of Poisson brackets. So in other words, we do get lots of Poisson brackets from specializations, but we never compute them. We just use the perfect pairing in order to prove results for them. So now, just to finish everything, we're in the world where we have this group GQ with semi-simple algebraic group of adjoint type, and BQ plus and BQ minus are the positive and negative Borels. So then the product of BQ plus and BQ minus in a way can be identified with a Zariski open subset of GQ, where the pair B plus and B minus is mapped to a product of B plus and the inverse of B minus and some operation on the Cartan part. And the last theorem is that if we look at the symplectic leaves of these BQ plus and BQ minus, they're precisely in bijection with the conjugal sequences of GQ under this isomorphism times points of this extra torus that appears on the top of the slide. And in other words, if we look at these finite dimensional quotients of the large quantum groups by all possible maximal ideals, these algebras are isomorphic across each conjugal sequence. So we still don't know what are the irreducible representations of these algebras, but we can say that there is an invariance along conjugal sequences, which sort of drastically reduces the complexity of the problem. And the picture is even better for the large quantum Borels. If we look at the maximal torus of this quantum Borel, it acts on these Poisson structures by preserving the Poisson structures. So if we're looking not just at the symplectic leaves, but at the torus orbits of symplectic leaves, we actually get finitely many of them. So if we were to study the irreducible representations of these quantum Borels, then we will look at these factor algebras, quantum Borel mod M times quantum Borel, and there will be only finitely many isomorphism classes of such finite dimensional algebras, and they will be precisely indexed by the elements W, by the Weyl group elements W of this adjoint algebraic group GQ. So if we look at this adjoint algebraic group GQ, we compute its Weyl group, then there are only that many different isomorphism classes of these algebras. We still don't know what are the irreducible representations, but from something that's totally infinite problem, now we reduced everything to a finite problem where we only have finitely many finite dimensional algebras for which we have to understand the irreducible representation. So that's all, and thank you so much for having me again.
Okay, questions? So I do have a question.
Yes. I would like to know if you did some computation of the radical of these algebras.
That's a great question. So we don't understand yet how exactly these finite dimensional algebras look like. So the thing that we're thinking of doing now is completely describing these finite dimensional algebras in the case of super SLMN type, where we will compute the radical, the semi-simple part, and that will give us exactly what are the irreducible representations. But that's exactly what we are thinking of doing next. So far, we don't know much about what is the structure of these finite dimensional algebras. We only know that there are finitely many of them that are needed to solve the problem. Thank you. It's a great question. So that will be definitely the next step that we're looking at.
Okay, thank you.
I do have a question. So this GQ is the algebra group related to the set of Cartan roots?
Precisely. Precisely. So the root system, that's again a great question, and you sort of almost answered the question. The set of the root system of GQ is precisely the root system that you obtain for the Cartan roots for the corresponding Yetter-Drinfeld module. Precisely, that's precisely what's the meaning of GQ. And here is the one of adjoint type that plays a role.
Okay. And something that I don't understand, these algebras UQ mod M UQ. Are they related? Like, if you have Q and P in same right conjugacy class, are these algebras related somehow?
If you have what in the same conjugacy class?
Q and say another braiding matrix P or something.
Not really. So I think that one is obtained from the other by certain twist. So these are not exactly the same algebras. That's my understanding. So when you change the matrix Q, the braiding matrix Q in certain situations, one algebra is going to be a twist of the other algebras. And my feeling is that these algebras, it's definitely going to be true for these last algebras here. These are going to be twists of the other, but I don't know how exactly everything would work over here, because in general, when we do these ideals here, I believe that the grading is still there, so we can still do the twist. However, over here, like for general conjugacy classes M, that might not be true. So it depends whether we can find concrete representatives in these conjugacy classes. But again, that's a great question. So the question is, how is this set of finite dimensional algebras, how does that vary when we perform certain operations on the braiding matrix?
Sorry. There more questions? I do have another question, but maybe, yeah, maybe we should stop recording now and thank Milen again. So thank you, Milen.
Thank you so much for having me.